Explainer code. Rationalizing the patches generated by automatic program repair tools using natural language explanations. I am Gimhan Sandipta and my colleagues are Ruan Ranasinghe and Swan Sankacha. Supervisors Dr. Sandareka Vikramanayaka, Dr. Nisansuthi Silva, Dr. Ridwan Sharifdeen. This diagram indicates the dataset creation methodology. Since no existing dataset combines bug fixes with natural language explanations for explainable program repair, and human annotation of the explanations for code fixes are expensive and time-consuming, we have introduced a methodology to generate the dataset utilizing existing high-end LLMs and apply rigorous validation process to ensure the quality of the dataset. As we can see in the diagram, first we select MegaDiff as our source dataset, which contains Java buggy programs and fixes. Then we calculate explanations for each pair of buggy fix pairs from two different LLMs, GPT and Cloud. Random 100 data points are chosen and calculate human agreement based on the Likert scale questions by three raters. Semantic similarity calculation is done for all the data points. If the semantic similarity of a data point is above the calculated human agreement threshold, such points are taken to the training dataset and other data points are discarded. The idea here is that when two different LLMs say the same thing, then the probability of it being a correct one is higher, and the LLM saying two different things means probably one of them or both of them are incorrect. On the left side of the diagram, we can see the APR tool, which takes the buggy code and processes it through a series of layers to generate a fixed version of the code. During this patch generation process, as the buggy code flows through the model, it produces rich internal representation at each layer. What we do is extract the self-attention input vectors from the last L layers of the APR model. These vectors capture important contextual and structural information about the code. We then inject these intermediate code-rich embeddings into the explanation generation pipeline on the right side. This part of the model, also referred to as the fix explainer, uses those representations to produce natural language explanations that describe the fix and why it's appropriate. Importantly, this process is performed for each of the last L layers, allowing the explanation model to benefit from multi-layered, context-rich information from the APR side. We also introduce gating parameters to control how much information is transferred from the patch generation to the explanation generation. Those gates help regulate the flow of information and ensure smooth and effective training. This slide explains the adapter module, which connects the code repairing model with the explanation generation model. On the left, we can see the architecture of the cross-attention mechanism. The adapter module is responsible for allowing the explanation model to focus on the internal representations coming from the APR model. We introduce new linear layers to project the output from both models into query, keys, and value vectors, which are then used to perform multi-head cross-attention. These linear layers are randomly initialized and need to be trained from scratch. The output from each head is then concatenated from the cross-attention output, which is used by the explanation model to guide the generation process. The key idea is that each token in the generated explanation can attend to all code tokens coming from the repairing model. As shown on the right side, this allows the explanation model to look back and attend to various parts of the original code context, enabling more accurate and context-aware explanations. Let's now look at the model choice for our system. For the automated program repair tool, we use Repair Llama, a 7 billion parameter quantized model enhanced with LoRa adapter layers. This model achieves state-of-the-art results in program repair, demonstrating strong internal code understanding. Thanks to quantization, It also reduces memory usage and computational cost, making it efficient for practical deployment. Once the code is fixed, we move to the explanation phase. For this, we use Llama, an 8 billion parameter instruct model trained on both natural language and code. This makes it ideal for generating human readable explanations of the repaired code. As shown in the diagram, Repair Llama processes the buggy code to generate the fixed version. This is then passed through an adapter into Llama, which produces the corresponding explanation. These two modules can work together smoothly, allowing seamless transitions and shared attention between code and explanations. This is our fine-tuning process we followed for both the Repair Llama and Llama models. We start with model initialization. For Repair Llama, we use the same architecture as the base model, while for Llama, we use modified architecture, so any new components are initialized from scratch. Next, we load the pre-trained weights, but importantly, we only unfreeze the newly initialized weights during training. The rest of the model remains frozen to preserve the already learned knowledge from pre-training. This helps retain the model's strong performance on general code and language understanding, while adapting only the parts necessary for our specific task. We also use LoRa layers for fine-tuning the attention modules, which is more efficient in terms of memory and training speed. On the environment side, we fine-tune using NVIDIA A40 GPUs with 80 GB RAM and CUDA 11.8 and train for 5 books with batch size of 16.
So now we are going to demonstrate our plugin. So for that, actually, we have used some Java buggy codes that we are going to use for the demonstration of our plugin. So let's first uh, call our plugin. So our plugin name is Fix Java Bug with Bugs Plain, Fix Plain. So we'll run it. So here you can see it's currently running. So typically it takes about like 10 seconds to run and it will generate the fix and the explanation. Yeah. So here you can see like it have highlighted the buggy code and it have fixed the bug in the fix code and also it have generated the explanation. So you can clearly see what was the bug that was fixed. So like if you need, if you can clearly like apply fix, that means you are accepting the fix and for example, when we click the apply fix button, the fix is automatically updated. So let's revert back. Okay. Here, if you want to like edit and fix, that means like if you are not satisfied like with the fix, so you need to change and like apply the fix, then you can like edit and apply the fix. So you can like need anything like a thing, you can add that thing and apply the edited fix. So let's go through another bug. So in a similar fashion, we'll trigger the extension on this buggy code. So this also will take about like 10 seconds. So meanwhile, I'll explain what is exactly happening in our backend. So actually, this is the train model that we are currently running in a Kaggle notebook. So what is happening is actually the extension. The extension will provide the buggy code for this server, and the server will like process the buggy code and will generate the fixed code and explanation, and it pass it to the front end of the extension. So as in here, so the 10 seconds have been passed. So as in here, it have like showcase the bug in the code, fix, and the explanation in the similar fashion. So what's exactly happening when we give this buggy code and this buggy code is sent to the server itself and it will generate the fix code and the explanation accordingly. So with that, actually, we can conclude our session.
Thank you.